Welcome back. This is the Unit 5 test corrections video. This is the calculator section of the test, numbers 9 through 15. Question number 9. The trick to question 9 was just the integral properties. Once you realized that the integral we're trying to evaluate is in a sum of an integral that we know how to evaluate and a number, we split this into two, and we treat the number like a function to evaluate it. A lot of people made the mistake of just adding 1. You can't just take out a constant at the back. There's a constant multiplier rule. If I was multiplying 2 times f of t, I could have multiplied the answer to the integral. But that's not what's going on here. What's going on is that we're adding the function 1. So you do need to take the integral of it. Best way to think about that is think of it as a rectangular area. There's a line that's 1 unit high, and it stretches from -4 to 3. The area under that line is a rectangle with a width of 7 and a height of 1. That makes the total area 6 plus 7, which is 13. Go ahead and try this one. And this is a t right here at the end, so it's f of t minus 2t dt. And the correct answer is E. Again, you use integral properties to split the integral, and then you need to take an antiderivative. This time, this is less easy to evaluate by area. So if you just take an antiderivative, you can still evaluate that at 3 and at -1. Remember that squaring it makes this positive, so you subtract the 2, and then when you subtract the subtraction of that, this flips to a positive, which gives you a total of 0. Possibly surprising, but that's what it is. Question number 10. Question 10 was a fundamental theorem of calculus problem. We have the function g of x, which is defined using an integral. So we want to take the derivative of g of x. Well, the first derivative of g of x is x squared minus x over x, and that's by the fundamental theorem of calculus. And that's because the function inside is the derivative of the function outside. So if I want the second derivative, I start with the first derivative and I take the derivative of that. You could have used quotient rule and you should have still ended up with the right answer, but the easiest thing to do is actually to recognize that this derivative can be split into two fractions, x squared over x and x over x. X over x is 1, x squared over x is x. So really this function is just a fancy way of writing x minus 1. The derivative of that is 1. Try this one. And the correct answer is E. I'm sorry about my typos here. Again, by the fundamental theorem of calculus, the derivative of the outside function of the integral defined function is just the inside function. And when you take the derivative, this maybe should say, sorry, sine of x squared, but when you take the derivative of that, you use just a chain rule. And so it's 2t cosine t squared, or 2x cosine x squared. Question number 11. Question number 11 was an equation. I might not have recognized right away what to do. This is one where you kind of have to work with what you understand. For what value of k? So the answers represent k values. So k is just a number. And for what number in the k position, which is the top of the integral, does the answer to this integral equal 0? Well, if I pretend in my head that k is a number, I can evaluate this integral and plug in k just as if it was that upper limit of integration. And I do that using an antiderivative. So the value of this integral must be 1/4 k to the 4th minus 1 over 4. And if it's supposed to equal 0, I can just solve that equation to figure out what k should equal. And it turns out k should equal 1. Use that same idea, the idea of setting up an equation using some sort of integral knowledge, to solve this one. And there is a slight difference in this, but I think you can figure it out if you think through what you're looking at. The correct answer was C, which is 12, and here's the work. So in this case, k is still a number, but it's actually a number inside the integral. If I pretend like it's a number and evaluate using an antiderivative, I can plug in 4 and 2, and I actually just went ahead to simplify that expression before I set up the equation. So negative k over 4 minus negative k over 2, if you add the two fractions, get a common denominator, actually ultimately equals k over 4. And so if k over 4 has to equal 3, k must equal 12. Question number 12. Question 12 was an average value. And I've got the work kind of awkwardly off to the side here, but maybe you can see it. We're given a function in an interval, and this is something you really should just end up putting in your calculator. The average value formula says 1 over b minus a. Remember, this is like dividing by the width. Starting with the area, the whole thing is going to equal the height, which is what the average value means. You're dividing by the width of the entire interval. So if I just plug in 2 and 0 and the normal function, I can evaluate this integral just using my calculator. When I did that using Math 9, I got 1.74159. Divide it by 2 and it gives you d. And the answer to this practice problem is B. If you need to see the B, there it is, 2.118. And then again, that's just like a quick calculator thing. Even though it's a weird function, you don't even need to worry about the integral. Question number 13. Question 13 was another fundamental theorem of calculus, and then you also had to use some analysis. I think this was probably the hardest multiple choice question on the test. But if you go piece by piece, I don't think it'll be confusing for long here. So g of x is a function. It's the integral of this other function. In other words, it's the antiderivative. We talked about it today in class. Understanding that g of x is a function, we can think about what it means to be increasing. Well, a function's increasing if its first derivative is greater than 0. And so we need to know what its first derivative is. Luckily, the fundamental theorem of calculus makes that really easy. The first derivative of a function defined as the integral of another function is just that other function. So cosine squared of x plus 1, that's the derivative. And if we want that derivative to be positive, we could think about it graphically as being above the axis, or we could solve it algebraically. I think if you have a calculator, the easiest kind of first step is to graph it. And when I graphed it, ignore the stuff down here, I actually saw that the curved line of the derivative function was above the x-axis the entire time, which means the derivative is always positive, which means the function g is always increasing. If this had crossed the x-axis, then any interval where it was below the axis would have been a place where it was decreasing. So I would have written intervals for all the places that the graph was above the axis. I just got lucky in this case. Try a similar one. Make sure you read carefully because it's not exactly the same. Same idea though. The answer for this one is C. And you could do it graphically or algebraically. It was actually pretty easy as long as you understand that the derivative of that big F is the inside function, x squared minus 9. This is a parabola that starts down on the y-axis at -9. If you think about the roots of this function, they're going to be 3 and -3 because those are the two numbers that make the function equal 0. And so knowing that those are the roots, you could just look at the graph and say, oh, well, between -3 and 3, the function's under the axis. In other words, the derivative's negative, which means the function's decreasing. Or you could solve it actually out algebraically, again, setting the function less than 0, setting the derivative function less than 0. Question number 14. Both 14 and 15 are questions that use a graph. It's really important that you realize that this graph is v of t, not f of t. We can, now that we understand fundamental theorem of calculus, we can understand this to be the derivative graph, if you like. So f is the antiderivative of v. In other words, it's the function defined by the integral, which also means that v of t is the derivative of f. You know that. The question's asking us to evaluate f of 3. Well, we don't have the f function. We don't have an equation for it. So I can't just think about what that means directly. What I can do is I can use the integral to define what the output of the function should be. If I plug in 3 for x in the integral, this isn't just a fun notation, it actually has meaning. When you put the 3 in there, the meaning of this integral is the area under the v graph, which we do see, between 0 and 3. So it's kind of an indirect way of figuring out what that other function, what its output would be. In order to actually find that area, you go from 0 to 3. You probably would recognize it's a triangle and then a rectangle together. The triangle's area is 3, the rectangle's area is 3. Add them together, you get 6. Try this one just like it. All right, my graph wasn't perfect, but the correct answer is B, and I'm going to try and keep the graph on screen here. F of 4 is what we're trying to find, so we just evaluate the integral that's given to us, and that's just the definition of f. When I plug in 4, we're now talking about the area under the graph between 0 and 4. From 0 to 4 is this triangle right here. I, in my head, split this into two triangles, although I'm looking at it a second time and I realize you could just do a single triangle. You could have done 4 times 2 times 1/2. But for whatever reason, when I was doing this, I did 2 times 2 times 1/2 as a small triangle and a second small triangle. Either way, you get 6 as your answer. Question 15. Question 15 is related to the same graph, which I can't totally show you, so I'm going to try and zoom it back and forth here. So what you need to recognize, again, is that if f is the integral of v, then f prime, the derivative of f, is actually just v itself. The derivative of the big F function, which is this function, is just v of t. That's the fundamental theorem of calculus. So to evaluate the derivative at 3, we actually just plug in 3 to the v function, which is the function we see. When you plug this in, you read out the output as the height of the graph. So if I go to 3, the v function has an output of 3 at 3, which is why the answer was A. Go ahead and try your last one. Oh, where is it? Here we go. Right, so unfortunately this is like literally the same thing. I was trying to make it slightly more interesting. Again, h is the outside function. That's kind of not a good way to put it. Let's call it the antiderivative. H is h. G is the derivative of h. In other words, h is the integral of g. If we want to evaluate the derivative of h, it's the same thing as evaluating g. If I plug 12 into g, it means I'm just reading the y value of g off of the graph, because this is the graph of g. So if I go to 12 on the x-axis and I go up, the y value is 6. You might have been tempted to find the area under the graph. Think about the fact that this is g. What would the area under the graph be represented as? Right, it would be the integral of g. In other words, that would be h itself, not h prime. All right, that's it for today. Have a good night.